Swayam Prabha. Digital India. Educated India.
I welcome you all to lecture number 28 on the topic radiation heat transfer. In the previous lecture number 27, we have seen the second mechanism or second mode of heat transfer, which is convection heat transfer. So let's recollect what we have discussed in that session. Convection is the second mode of heat transfer. Before that, we have studied about the conduction mode of heat transfer. So in conduction, it is due to the vibration of the molecules. The heat is flowing, and in convection it is between a solid surface and a fluid. It need not be between a solid surface and fluid only, it can be the other fluids also. However, the mechanism is due to the movement of the molecules. So there should be molecular motion. So the convection is classified into two types primarily: natural convection or free convection, and forced convection. In case of natural convection, as the name indicate, the convection takes place naturally. That is due to density gradient. Like when a fluid comes in contact with a hot surface, so the molecules which are attached to the surface, it gets heated. So when a fluid is heated, it becomes lighter, so it rises upward. So there is a density difference between the hot fluid and the cold fluid. So due to this density gradient, density difference, the natural convection occurs. In case of forced convection, we use a external device, it's a fan, to circulate the air with a velocity, with a particular velocity. Of course, the velocities can be varying also. So by means of an external means, the convection is made to happen. So that is, it is forced to happen, so it is called a forced convection. There are two non-dimensionless non-dimensionless numbers which we have seen. In case of forced convection, it is Reynolds number, it is the ratio of inertia force to viscous force. And in case of natural convection, the Grashof number is used. The inertia force is replaced by the force due to buoyancy. And for an external flow, if the value of Reynolds number is less than 5 into 10 power 5, this is for an external flow, then we call that flow as laminar. And if the Reynolds number for an external flow is greater than 5 into 10 power 5, then such a flow is called as turbulent flow. At a Reynolds number of 5 into 10 power 5, the flow changes from laminar to turbulent. There is a transition. However, this value is this Reynolds number is the value of Reynolds number differentiating the laminar and turbulent flow. In case of an internal flow is different. If it is less than 2300, we call it as internal, the laminar flow in case of internal flow, and if it is more than 2300, that is called as turbulent flow. Then we have seen the concept of boundary layer, layer which is formed during if you take the thickness of the boundary layer. In case of velocity boundary layer, there is variation, there is a velocity gradient. So the thickness of the velocity boundary layer is denoted by the letter delta, and there is one more boundary layer that is due to temperature gradient. That is represented by delta T. So in case of velocity boundary layer, after a particular point in the boundary layer, that is in the direction normal to the flow, so the thickness, the velocity of the fluid will be equal to the free stream velocity. Similarly, in case of thermal boundary layer, temperature difference between at any point and the surface temperature will be equal to 99%, that is 0.99. into the delta t value. That means after that particular point there will not be any change in, there will not be there will not be any temperature gradient. And when there is a velocity gradient, as per the Newton's law of viscosity, there is a shear stress which is developed. Tau is equal to mu into du by dy, where mu is the proportionality, the term, the parameter which is used to remove the proportional term. Tau is directly proportional to du by dy. Du by dy is the velocity gradient. Mu is termed as viscosity or dynamic viscosity. The ratio of dynamic viscosity to the density of the fluid is termed as kinematic viscosity, which is another viscosity. And based on this boundary layer and also the convection heat transfer, we have solved quite few numerical questions, and especially the boundary layer numerical question, we have used the correlation which is given in the heat and mass transfer data book. I have used the heat and mass transfer data book published by the author Godan Raman and Subramanian, the 9th edition. So in case if you are referring the latest version of this published by the same authors, so there may be slight change in the page numbers, not much change, maybe plus or minus 2 or 3 pages differences will be there. Now let us move to the contents of this lecture number 28. We will see the third mechanism of heat transfer, that is radiation heat transfer. Introduction, thermal radiation, black body, Stephen-Boltzmann law, emissivity, the difference between absorptivity, reflectivity and transmissivity, and a few numerical questions. So radiation is the mechanism, heat transfer mechanism, which takes place without the presence of a medium. So unlike conduction and convection, it requires a medium for the heat transfer to take place, whereas radiation does not require a medium. It can occur two bodies separated by a medium colder than them, it can occur. So for example, if a person is standing in front of say the wood is burnt, this one during severe winter or when the temperature is very less, so people used to just burn some wood and just warm their body. So whatever when they do that one, so the distance the distance between the fire which is coming out of that wood and the person, the human who is standing, so the air in between them, the temperature of that medium may be different. In spite of that, there are possibilities of radiation from this one. So that's what it can occur between two bodies, that is of radiation from the fire which comes out of burning of the wood and the person who is standing, in spite of the fact that the air between them may be at a different temperature. Examples are the energy which we receive from the sun every day, that is in the form of radiation, and the heat transfer from the object which is placed in a vacuum. Of course, in vacuum there are no possibility of the presence of molecules, so there is no medium. So the only mode of heat transfer which could take place in vacuum is radiation, where there is no presence of medium. Now let us see thermal radiation. Thermal radiation is nothing but the radiation only. The wavelength of if we see the electromagnetic radiation spectrum, the range, it's from say 10 power minus 10 to 10 power plus 10. So the less than 10 power minus 9 micrometer, okay. So that cosmic rays, and it goes up to 10 power plus 10 and above maybe, that is for electrical power waves. So the wavelength in terms of micrometer varies from 10 power minus 10 to 10 power plus 10. Between this cosmic rays and electrical power waves, there are other components like gamma rays, X-rays, ultraviolet rays, visible light, visible region, infrared region. Then we have the radio waves, radio and TV waves, microwaves. Before the radio and TV waves, microwaves are there. Then radio waves, then we have the electrical power waves. Let me repeat it again. So, between the cosmic rays and the electrical power rays, we have gamma rays, X-rays, ultraviolet radiation, then visible region, visible light, then we have infrared radiation, microwave, radio and TV wave, and then we have the electrical power waves. So, the thermal radiation or the radiation, it is an electromagnetic form of radiation which is emitted by a body whose temperature is above absolute zero, absolute zero. Let us see how to define a black body. A black body is a substance or an object which absorbs all the radiation falling on it irrespective of the wavelength, and it does not reflect. So, a black body is a one which it is a perfect absorber. It is a perfect absorber. This is like a ideal condition. It is like an imaginary body. This is not like a real substance. So, it is a body or an object which absorbs all the radiation, and does not matter whatever the wavelength of the radiation which is incidenting on that body, it will absorb and it does not reflect. So, the reflectivity is a 0 for a black body. The amount of radiation absorbed is 100%. So, a black body is a perfect emitter and absorber of radiation. That is what I have mentioned here. Okay. Perfect emitter and absorber. The amount of radiation emitted depends upon the temperature and the surface properties. It depends upon the roughness of the surface, it depends upon the properties of the surface, and also its temperature, So, this is the law which governs the radiation. So, if you see the laws which governs the various modes of heat transfer or various heat transfer mechanisms, if you take conduction, the governing law is Fourier law of heat conduction. That is, the rate of heat flow is directly proportional to the temperature gradient. So, if we remove the proportional term symbol, the constant which is used called the thermal conductivity of the material, which is used to construct that particular configuration. It could be a wall or a cylinder or a sphere, etc. So, Q equal to minus Ka dt by dx, and minus sign indicates that the heat flow is in the positive x direction. And in case of convection heat transfer, the governing law is Newton's law of cooling. Q is directly proportional to the A into delta T. Of course, A heat transfer area remains constant. Delta T is the difference between the surface temperature and the fluid temperature. So, in order to remove the proportional symbol, the constant which is used is heat transfer coefficient due to convection, that is small letter h. So, it is in watts per meter square Kelvin. So, Q equal to HA delta T. When if we divide Q divided by A, capital Q divided by A. So, whenever I have said this Q equal to minus Ka dt by dx or Q equal to HA delta T, the Q is capital letter alphabet Q. Small q is nothing but heat transfer per unit area. Small q equal to capital Q by A, which is termed as heat flux, watts per meter square. Capital Q is watts, small q is watts per meter square. Small q equal to capital Q by A. And let me emphasize once again that the internal heat generation, that is expressed in Q dot, that is amount of heat generated per unit volume. It is watts per meter cube. So, there are 3 Q, one is capital Q, one is small q, another one is small q dot. Now, coming to this the governing law for the radiation, which is the Stephan-Boltzmann law. So, it is the radiation emitted by a black body, per unit time and unit surface area, okay, per unit time and per unit surface area. So, this is very important, per unit time and unit surface area. It is directly proportional to the 4th power of the absolute temperature, T power 4. So, here temperature should be substituted in Kelvin, not in degree centigrade. It is T into T into T into T, that is 4 times. Okay. So, this is the absolute temperature, where E suffix B is the emissive power of a black body, which is in watts per meter square, because we are defining this law per unit surface area. So, per meter square, per meter square. So, per unit time, that is joules per second. So, it is not in joules, joules per second. Joules per second is watts, and when we divide by the unit area, it becomes watts per meter square. And sigma is called to remove this proportional symbol, the constant which is used is called Stefan-Boltzmann constant. So, it is as a constant value 5.67 into 10 power minus 8 watts per meter square Kelvin power 4. Because we have T power 4, so here we have got Kelvin power 4, Kelvin power 4. So, this is, okay. So, this K power 4 is there only for Stefan-Boltzmann law, and the temperature T is the temperature of the surface. Now, let us define the term emissivity. So, emissivity is the ratio of amount of radiation emitted by a surface, by any surface, to that of the radiation emitted by a reference surface, which is the black body. So, E divided by EB, E is the amount of radiation emitted, okay. That is capital E. E, when I say E suffix B, it refers to the radiation emitted by the black body, which is taken as the reference. So, this is EB is proportional to sigma into T power 4, we know that one, and that is the Stefan-Boltzmann law, which is the governing law for the radiation heat transfer. And to remove the proportional, the constant used is Stefan-Boltzmann constant, which has a value of 5.67 into 10 power minus 8 watts per meter square Kelvin power 4. Let us see the terms, the difference between the terms absorptivity, reflectivity and transmissivity. Okay. So, here this is the surface on which, this is the surface on which the radiation is falling, radiation is falling. So, the total radiation which is falling on the surface, so the amount of radiation which is, okay, I have used the alphabet or this letter which is used in the standard textbooks, capital G, that is the radiation incidenting on the surface, it is incidenting on the surface. So, some of the radiation is reflected, which is shown in purple color, some amount of radiation is absorbed, which is shown in blue color, okay. This is shown in blue color, that is absorbed, and the remaining portion of the radiation is transmitted, which is shown in this sandal color, cream color, okay. So, radiation is falling on, incidenting on the surface, not all the radiation is reflected, not all the radiation is absorbed, not all the radiation is transmitted, if you go by this schematic, okay. So, the purple color represents the amount of radiation reflected by the surface, the blue color represents the amount of radiation absorbed by the surface, and the sandal color, okay, which represents the amount of radiation transmitted through the surface, transmitted through the surface. So, the amount of radiation absorbed, I am taking G suffix A, because G is the radiation which is falling on that one. So, out of the radiation which is falling, only a fraction is absorbed, so it is GA. Similarly, out of the radiation which is incidenting, a fraction of the radiation is reflected, so reflected is R. So, I am using the symbol GR, and the amount of radiation transmitted is GT. Now, based on this, absorptivity, absorptivity is the amount of radiation absorbed to the total radiation, that is GA by G. Similarly, GR by G we can find out, G suffix T by T, that is the amount of radiation reflected to the total radiation falling on the surface or incidenting on the surface. Similarly, the amount of radiation transmitted to the total radiation incidenting on the surface. So, GA by G, that is called absorptivity, it is represented by the letter alpha, this is alpha, okay. And amount of radiation reflected to the total radiation falling on the surface is reflectivity. The amount of radiation transmitted to the total radiation incidenting on the surface is transmittivity. Absorptivity is alpha, transmittivity is rho, reflectivity is rho, transmissivity is tau. Let me remind, this is not a proportional term, this is alpha, that is the Greek alpha, but rho is not the density here, rho is the reflectivity. These are all the standard letters used to represent these these properties. Okay. So, when we add the amount of radiation absorbed plus reflected plus transmitted, this will be equal to G. Okay. So, it may be 40% absorbed, 25% reflected, the balance 35% may be transmitted. It can be, the numbers can be different, but the sum of all these three terms Ga plus Gt plus Gr will be equal to the total radiation falling on the surface. So, now I am dividing this, the left hand side and the right hand side by the total radiation term, which is capital G. So, Ga by G, this is Gr by G, right side will become G by G, that is 1. So, this Ga by G is nothing but alpha, which is called absorptivity, and Gr by G is called rho, that is reflectivity, and Gt by G is called transmissivity tau. So, that means the sum of absorptivity plus reflectivity plus absorptivity will be equal to 1, or in other words, the amount of radiation reflected plus amount of radiation absorbed plus amount of radiation transmitted will be equal to the total radiation incidenting on the surface. Okay. So, for an opaque surface, it does not transmit any amount of radiation which is falling. So, tau is equal to 0. So, if you put tau equal to 0, then the summation of absorptivity and reflectivity will be equal to 1, this is applicable only for an opaque surface. So, with this background, let us solve the numerical. So, if you see before this one, if you take the electromagnetic spectrum, so as I explained before, so the range it is from 10 power minus 10 to 10 power plus 10, which varies from cosmic rays to electrical power waves. So, in that if you take there are different components are there, like ultraviolet radiation, infrared radiation, X-rays, gamma rays, radio waves, microwaves, all these things. I will just give some examples like this. This X-rays, this gamma rays are the example is the nuclear reaction. Then the X-rays, that is due to the bombardment of the metal with electrons, high energy electrons. So, that is how these X-rays are generated. And if you take microwaves, so these waves are generated by an electron tube called magnetron. So, those it is a device which develops or generates these microwaves. That is the, if you take the micro oven example. So, when we just open the oven and keep the food items and just allow it to be heated for some time, when we switch on, so the food is cooked due to the generation of this microwaves, and of course, above microwaves we have the radio waves and the electrical power waves. So, I just want to tell these few examples, like how these X-rays are generated, how the gamma rays are generated, how the microwaves are generated. Example is the microwave oven. Now, let us see the first numerical. A spherical ball 20 centimeter diameter at a temperature of 800 Kelvin, the temperature is given in Kelvin, not in degree centigrade, is suspended in air. So, a spherical ball is just like it is hanged in the air like this. I will show the diagram. The next slide. Assuming the ball has a black body, determine the emissive power and the amount of radiation emitted by the ball in 5 minutes. So, it is a very simple numerical. Diameter of the ball is given, so we can find the radius. Okay. Diameter is given as 20 centimeter. That means radius equal to diameter by 2, that is equal to 10 centimeter. Okay. Temperature is given as 800 Kelvin. temperature is given as 800 Kelvin. Okay, so let us convert this into meter, divide by 100, converting centimeter into meter. Time, okay, so we have to find out the amount of radiation emitted by the ball in 5 minutes. So that is 300 seconds. So these are all the data given, 5 minutes, 300 seconds. Okay. So it's a very simple one. The question number 1 is determine the emissive power of a black body. So we can use the Stephan-Boltzmann law. Okay, we can use the Stephan-Boltzmann law, sigma into T power 4. This is the first part of the question. Emissive power of a black body. Okay. So Stephan-Boltzmann law, Stephan-Boltzmann, Stephan, not Stephens. So Stephan-Boltzmann law. Okay. So emissive power of a black body is proportional to T power 4, fourth power of the absolute temperature. So that is sigma into T power 4. This emissive power, it is the amount of radiation emitted per unit time, per unit area. So that means it is in watt per meter square. Now the sigma is equal to 5 into 5.67 into 10 power minus 8. Temperature is given 800 Kelvin. So 800 to the power of 4. Here temperature should be in Kelvin only. T is in Kelvin. It is not in degree centigrade. This is very, very important. Temperature should be in Kelvin only. So the Stephan-Boltzmann constant will not be given. So we have to remember this value and substitute. So 23.2 kilowatts per meter square. 23.2 kilowatts per meter square. Now amount of radiation emitted. This is first one is the emissive power, amount of radiation emitted, that is Q radiation. So next one is the Q radiation. Okay. So we will use this formula. So this is here I have E suffix B, that is the emissive power of a black body. It is in watts per meter square. Okay. So the amount of radiation should be calculated in terms of joules. So watts per meter square, if we multiply by area, so we will get it in watts. Watts is in joules per second, multiplied by time in seconds. Second and second will get cancelled, we will get the answer in joules. Okay. So Q of radiation is equal to the emissive power of a black body. This is in watts per meter square into area in meter square into time in seconds. Time in seconds. So this is equal to emissive power of a black body into, so this is for your understanding I am writing these units. Okay. So the formula is E suffix B into A into T. So this is the formula. Okay. Whatever I have written in the bracket, that is the SI units to make you understand. So this is in watt per meter square, watts is joules per second, second and second will get cancelled. So we will get the amount of radiation in terms of joules, and the area is 4 pi r square. If you see it is a spherical ball. Okay, a spherical ball. Surface area of a sphere is 4 pi r square. 4 pi r square. So this is the surface area of the sphere. Surface area of the given configuration. Which is nothing but sphere. So 4 pi r square into T. So all the values we know. We have calculated E suffix B 23.2 into 4 pi r square. Okay, or you can substitute in the diameter also, r equal to d by 2. So it will be d square by 4. Okay, pi by 4 d square into time in second. This should be in seconds. So the amount of radiation is 876 kilojoules. 876 kilojoules. So here let me again explain the units. Watts per meter square. Okay. into meter square into seconds. So, meter square and meter square will get cancelled. So, watts into seconds, watts is joules per second into second. So, joules. So, we get the answer in joules, we get the answer in joules. Let us move to the second numerical. Consider a cubical furnace, the dimensions of the furnace are given. Okay. So, you know the sides of the cubes are equal. So, 5 into 5 into 5 meter in this case, whose surfaces closely approximate the black surface. The base, top and side surface of the furnace are maintained at 3 different temperatures, that is the base is maintained at 800 Kelvin, top surface at which has got the highest maximum temperature 1500 Kelvin, and the surfaces on the side surface are maintained at 500 Kelvin. Determine the net rate of radiation heat transfer between the base and the side surface first. This is the base, this is the side surface. The second one is the base and the top surface, and from the how much heat is lost or what gained, whatever it is, from the base surface. So, this is the diagram T1. Okay. So, this is the base, this is the side, and this is the top surface. This is the top surface. So, I am taking the temperature 1 for the base and T2 for the top surface and T suffix 3, that is for the side surface. So, that is what I have written here. T1 is the temperature of the base 800 Kelvin given, T2 is the temperature of the top surface, that is 1500 Kelvin. Okay. T1 is the temperature of the base, that is 800 Kelvin, T2 is the temperature of the top surface 1500 Kelvin, and T3 is the temperature of the side surface 500 Kelvin. So, these are all given data. Okay. So, these are all the data given in the problem, and the dimensions are given. So, it is a dimension of cube, dimension of cube 5 meter into 5 meter into 5 meter. Okay. So, length, width, okay, and for height we use the term d. I will tell you why the symbol d is used, because we are using the data book to solve this problem. So, whatever the symbol which are used. So, here if you see here, okay, so this is the length, this is the length, this is the b dimension. Okay. So, it is given length and like length, width and height. Height is, that is distance from the base to the top, that is mentioned as d. It is not diameter, it is the vertical height between the base and the top surface. Okay. So, that means this is L. Okay. L is, this is like L into B into D. Okay. This is the vertical height, vertical distance, okay, vertical distance between the base and top surface Okay. So, net rate of radiation heat transfer between the base, that is base is surface 1, top is surface 2 and side is surface 3. The first question is between base and side surface, that means between surface 1 and the side is surface 3. So, I am using Q13. Okay. So, Q between base and side. Base is surface 1 and side is surface 3. So, because we have to find out between base and side, base and top. So, if you write Q, we will not be able to differentiate. So, between base and side it is written as, because surface base is surface 1 and side is surface 3, that is Q13, Q13. Okay. So, if you see the formula, A1 into, that is the area at the base, into F13, A1 into F13 into sigma, and the temperature difference between the base and the side, that means base is surface 1, side is surface 3, T1 minus T1 power 4 minus T1 power 4 minus T3 power 4. So, this is slightly modified form of the Stephen Boltzmann law. Okay. So, it is sigma into A into T, where T is there is a delta T between surface base surface and the side surface. And now this F is called view factor or shape factor or configuration factor. When I say F13, this shape factor for the, when the heat transfer is there between, due to radiation between surface 1 and surface 3, that is between base and side, that is the meaning. F12 means heat transfer due to radiation between the surface 1 and surface 2. So, this is the out of the fraction of energy which is leaving a surface, what is the amount that is striking the other surface. So, that is the meaning of view factor. It is the fraction of the radiant the energy leaving the surface I, in this case it is fraction of the energy due to radiation from surface 1 to the energy that is striking on the surface number 3, So, there are 3 names: view factor, shape factor, configuration factor, all are same. Now, this view factor, okay, F113, and if you take base, it is the plane, So, always for a plane surface, so it is how we are finding is F11, that is the base 1, then from surface 1 to 2 and 1 to 3. Okay, so if you take this diagram, so this is 1 1. Okay, so here shape factor F11, and from here to here it is F12, from 1 to 2 it is F12, and from 1 to 3 it is F13. That is view factor for the surface 13. This is view factor for the surface 12. Of course, this is base only. So, F1 or F11. So, since the surface 1 is a plane, the shape factor is 0. So, if you substitute it here, okay. So, this term is 0. Now, if I know F12, I can find F13. If I know F12, that is shape factor for the surface from 1 to 2. From the base surface to the top surface, I can find F13, because the summation is 3 equal to 1. Okay. Suppose if there is one more surface, so if you add that one, the total remains the 1. Now, this F12, it is taken, unless I find F12, I cannot find F13, because when I am calculating Q13, the formula is F13. Okay. Now, from heat and mass transfer data book, I have given the page number. Again, let me emphasize, I am using the 9th edition of heat and mass transfer data book published by C.P. Godanraman and Subramanian. Okay. So, according to that edition only the page numbers are given. So, L by D, what is L by D? L is the length portion of the cube. D is the distance between the base surface and the top surface, and B is the width or breadth of the cube. Okay. So, now, so the terms are used here. L, see, this is L, this is L, this is D, this vertical distance is D, and this is B, this is B. If the letters are not clear, I will just return. So, this is L. Okay. So, this is L. Okay, anyway, the arrow marks are clear. Now, here this is L by D, here it is L by D, this is all these values are L by D, and these horizontal are L by D, that is length by the vertical distance, and these vertical values are, this is, okay, let me write it here. These values are, the first column values are B by D, that is this dimension divided by D. Of course, for a cube here, I mean the sides of the cube are same, so it is 5 into 5 into 5. So, L by D is 1, okay. So, that is what I have written here. L by D, the dimensions are same, so 5 by L by D is also 1, B by D is also 1. Now, corresponding to L by D equal to 1, L by D is, this is here 0.1, 0.2, 0.4, 0.6, 0.1. So, this is L by D 1, L by D is 1. So, this is L by D equal to 1, and similarly B by D equal to 1 is this one, this is B by D. So, the intersection one is, I am getting this value, I am getting this value. So, that value only. So, in case if it is not clear, you can refer the data book, the hard copy of the data book or the magnified form of the soft copy, so that you can check, verify the answer which you are getting. It is, if it is rounded off, it is 0.2. So, L by D is the horizontal one, B by D is the vertical one. So, the intersection value is F122. Now, I have got F122. Okay. So, from HMT data book, okay, page number is also I have given, that is 101, page number is 101, page number is 101, page number 101 for L at L by D equal to 1, at L by D is equal to 1, at B by D is equal to 1. So, we are getting F12 is equal to 0.2. Now, the formula is F11 plus F12 plus F13 is equal to 1. So, this is 0 because surface 1, it is a plane surface. So, this is 0, F1D I have found out 0.2. So, the only unknown is F13 which is equal to 1. From this we can calculate F13 is equal to 1 minus 0.2, that is 0.8. So, now you have to substitute here. So, I have found F13 as 0.8, substitute here, Q13 will get 394 kilowatt. So, if you substitute this here, and calculate Q13 is equal to 394 kilowatts. Similarly, you can write the formula for Q122. Okay. Similarly, we can calculate the formula for Q122. Okay. A2 F122, if it is Q122, A2, and of course, sigma will be there. Sigma is 5.67 into 10 power minus 8, that is a constant value. And if it is 1 to 2, the temperature will be T1 power 4 minus T2 power 4. Okay. So, here it is Q1 to 3 means temperature 1, temperature 3. Q1 to 2 means T1, T2. So, now this value only we have taken from data book. This is from HMT data book. This is what we have taken from HMT data book. Okay. So, it is 1319 kilowatts, 1319 kilowatts. Similarly, you can find Q1 to 3. Okay. So, from the surface 1, so add this one Q11, Q12, Q13. So, you will get the net value. So, that is the radiation from the base surface. Due to radiation heat transfer from surface 1, which is striking the surface number 2, because this is for, see, shape factors, this is for shape factor F1 to 2, This is for equal parallel rectangles in opposite direction. So, only for that configuration this the page number of the data book can be used, not for if it is not meeting this requirement. Next, let us move to the third problem. A plate having 10 centimeter area on each side is hanging in the middle of a room. The room dimension area is given. So, the room area is 100 meter square. In that 100 meter square room area, a plate of 10 centimeter square area, it is suspended or hanging in there. Okay, so this, of course, this is the total surface area of the room. Okay, 100 meter square is the total surface area. The plate temperature and emissivity are given. The temperature and the emissivity for the surface of the room are also given. So, both the temperature and emissivity for the room as well as for the plate are given. Calculate the total heat loss from the two surfaces of the plate, that is on the both sides. So, this is the one. So, this is plate temperature T1 and the room temperature, of course, epsilon 1. Emissivity, the symbol used is epsilon. Okay. So, the symbol used is epsilon. So, let me when I explain the problem, I will see here this is emissivity. This is emissivity. So, emissivity is mentioned as epsilon. For room 1 it is epsilon 1 and for the plate it is epsilon 2. So, it is given as 0.6 and 0.3, 0.6, 0.3. Okay. So, this is here I am taking plate as a 1 and the room is as the number used to represent the room is 2. So, T1 refers to the temperature of the plate. So, that means epsilon 1 refers to the so that is the plate temperature is given, plate emissivity is 0.6. So, this is plate, this is room. Similarly, T1 is given and T2 is given. T1 is 800 Kelvin, T2 is 300 Kelvin. That means heat transfer is from the plate to the room, from the plate to the room. So, now we will be using this one because the emissivities are given. So, there is one formula mathematical expression which need to be derived, or we can directly use it. I have just given the procedure also. Heat loss from one surface of the plate is given by epsilon into T1 power 4 minus T2 power 4 for varying emissivities. The emissivities of both the surfaces are different. Okay, one has an emissivity of 0.6, another one has an emissivity of 0.3. And A1, A2 area is given. Okay, let me write that also. So, A1 is equal to 10 centimeter square. So, 10 into 10 power minus 4, 1 centimeter is 10 power minus 2 meter. So, square is 10 power minus 4 meter square. So, 10 into 10 power minus 4 can be written as 10 power minus 3 meter square, and the area of the room is given in meter square only. Okay, the surface area of the room is 100 meter square. So, this is the given data. Heat loss from one surface of the plate is given by this formula, sigma into T1 power 4 minus T2 power 4. Sigma we know 5.67 into 10 power minus 8. Sigma is equal to 5.67 into 10 power minus 8 watt per meter square Kelvin power 4, Stephen Boltzmann constant. Now, epsilon 1, this one. So, here, so the two surfaces are there. We are using the 1 for plate and the subscript 2 for room. So, shape factor from the shape factor for that is the fraction of energy which is radiated by the surface 1, which is striking the surface 2. Surface 2 is the room. So, that is F12. So, that is F12. There is only one shape factor involved in this problem. Okay. And for it is given by this one. So, for a like a parallel one, okay, for a parallel this one, the shape F12 is equal to 1. Okay. So, you can find this value in the data book. Okay. So, this is found in one of the pages in the data book. F122 is 1. So, this term will reduce to 1 by, this term will reduce to 1 by A1
the other terms there is one. So, take LCM for the first two terms in the denominator. So, if you take LCM for this term and this term, you will, and once you simplify you will get this one. So, the final the mathematical expression, that is this is, if suppose if you take this as equation number 1, it will be reduced to sigma into T1 power 4 minus T2 power 4. Okay. So, let me write this equation, sigma into T1 power 4 minus T2 power 4, the whole divided by, okay, the whole divided by 1 by A1 epsilon 1 plus, okay, 1 minus epsilon 2 A2 into epsilon 2. This is after taking LCM and after simplification. So, directly we can write this formula. Okay. So, here T1 T2 is given, A1 you know, epsilon 1 you know, all are given, all the values, all the 6 values are given, T1 T2 A1 A2 epsilon 1 epsilon 2. So, if you substitute, we will get the value as Q equal to 13.7 watts, 13.7 watts. This is from one side of the plate, So, we have been asked to find out, calculate the total heat loss from two surfaces of the plate, calculate the total heat loss from two surfaces of the plate. So, multiply by this value by 2. Okay. So, this is 13.7 watts is the amount of heat lost from one surface of the plate. So, for both the surfaces, therefore, Q for both surfaces is equal to 2 into 13.7 watts. Okay. So, that is 27.4 watts, 27.4 watts. So, that completes this numerical question. So, there is one more numerical question. So, two large diffused grey parallel plates separated by a small distance have surface temperature of, so the plate temperatures are given. Whenever we solve numerical question related to these two large parallel plates or this one, so it is considered to be infinitely long plates, not a short plates or medium configuration plates. So, the temperature of one plate is 400, the other plate is 300, emissivity of both the plates. In this case, the emissivity epsilon 1 is equal to epsilon 2 is equal to 0.8. Okay. Sometimes in other numerical questions, epsilon 1 will be different, epsilon 2 will be different. Even in the numerical question which we have solved now, here epsilon 1 is 0.6, epsilon 2 is 0.3. So, there is a two large parallel plates. Plate 1, I am using the suffix 1. Plate 2, because it is plate 2, the subscript used is 2. So, epsilon 1 is 0.8. In this case, both emissivities, the emissivities of both the plates are same. So, epsilon 1 is equal to epsilon 2. Temperatures are different, of course, T1 is 400, T2 is 300. So, heat transfer is from plate 1 to plate 2. Okay. So, let me write the given data. Plate 1, temperature 1 is equal to 400 Kelvin, emissivity is 0.8, and for plate 2, T2 is equal to 300 Kelvin and emissivity is same. Okay. Emissivity is same. So, I am taking the same formula which we used for the previous problem, the reduced mathematical expression. So, Q equal to sigma into T1 power 4 minus T2 by this one, because this is the one which has both the emissivities, different emissivities. Then here, but of course, in the numerical question which we are discussing now, epsilon 1 equal to epsilon 2, for the previous question it was different. So, I am taking this formula. Okay. See, for infinitely large parallel plates, okay, this is given in the data book. Okay. So, F for infinitely large parallel plates, F12 is equal to 0. Okay, F12 is equal to 1, not 0, shape factor is 1. For surfaces which are infinitely long, which are parallel, F12 is F12 equal to 1, and the area is this one, A1 equal to A2 equal to A. So, if we substitute this one in this equation and simplify, we will get this equation. Okay. Of course, A I have taken to the left side. So, Q is equal to sigma into A into T1 power 4 minus T2 power 4. Let me use the square bracket for the denominator, T1 power 4 minus T2 power 4. That is heat is heat transfer is from plate 1 to plate 2. So, T1 power 4 minus T2 power 4 divided by 1 by epsilon 1 plus 1 by epsilon 2 minus, I think minus 1, sorry, after simplification it is minus 1. So, we can directly write this formula, for parallel infinitely long plates, because the shape factor is 1, area remains same. So, if you substitute, we can directly use this formula, Similarly, for the previous question, we can directly use this formula, Now, here we know the value of sigma. So, we have been asked to find out heat transfer per unit area. Okay. So, if area is not known, we can find out, bring this A to the left hand side denominator. So, it will become Q by A. So, watts per meter square, which is nothing but heat flux. Okay. Sigma into T1 power 4 minus T2 power 4 divided by 1 by epsilon 1 plus 1 by epsilon 2 minus 1. So, this both the value, of course, here emissivity remains the same for both the plates. T1 is given, T2 is given, this we know. So, Q by A is equal to 661.5 watts per meter square, Okay. So, that completes the problem. Now, let me summarize. So, in this lecture number 28, we have seen the radiation heat transfer. So, primarily this mode of heat transfer or this mechanism of heat transfer takes place in the form of electromagnetic radiation. Okay. The example is the energy that we receive from the sun every day. Okay. And the radiation heat transfer is different from the other two, where conduction and convection mode of heat transfer requires a medium for the heat transfer to take place, which is not so in case of radiation heat transfer. The governing law is Stephen-Boltzmann law. Emissive power of a black body or the amount of radiation emitted is directly proportional to the fourth power of the temperature, and the temperature is in absolute, it is in Kelvin, not in degree centigrade. So, it is Q equal to remove the proportional term symbol, the constant used is Stephen-Boltzmann constant. So, Q equal to sigma into A into T power 4. So, if it is for two surfaces, T1 power 4 minus T2 power 4, and there is a factor which is introduced, that is called shape factor or view factor or configuration factor. There is a fraction of energy, that is fraction of energy leaving the surface 1, striking the surface 2, that is the meaning of F12, and we have solved the numericals also based on these the topics which we have discussed. So, with this, let me conclude lecture number 28. Thank you.